is 1 plus 2. Well, there are preferred combinations of neutrons and protons at which the forces holding the nuclei together seem to balance best. Now, the question is, can we put any number of neutrons in the nucleus? Well, the question is no. In order that a nucleus may be stable, there is a preferred number of neutrons and protons. And that's the reason why the ordinary hydrogen, which is the most abundant hydrogen, is just 1 proton. Now, light elements tend to have about as many neutrons as their protons. So if you look at elements that are light, that means atomic numbers 1, 2, 3, 4, 5, 6 and so on, they tend to have almost as many neutrons as there are protons. The number of neutrons will be equal to the number of protons in the nucleus. But as the elements become bigger, heavier and heavier, in order to keep the nucleus together, you need a larger number of neutrons. So atoms with too many neutrons or not quite enough can sometimes exist for a while, but they are unstable. You see, if a nucleus contains far too many neutrons or far too less, we will say such a nucleus is unstable and such a nucleus will simply disintegrate. It is materials like that we call radioactive materials. You see, that is not to say that elements can't have more than one stable isotope. There are. Now, ordinary hydrogen and deuterium are both stable, and you can see tin has 10 stable isotopes. You see, tin comes in 10 different forms. In other words, the nucleus can have 10 different combinations of protons and neutrons. All elements beyond bismuth, that is atomic number 83, are unstable. So any element that is above atomic number 83 is unstable, and they will be radioactive and they will disintegrate. If the combinations of protons and neutrons in a nucleus is not conducive to stability, then we say that nucleus is unstable. Now, as I told you, any nucleus above atomic number 83, that is bismuth, is that right? Any nucleus that has an atomic number greater than 83 is unstable. The combinations of neutrons and protons does not allow a conducive living together, or the stability of the nucleus is affected. We say such atoms are radioactive. What is the meaning of radioactivity? Such nuclei will throw away nuclear particles and energy. You see, and these nuclear particles and energy that are thrown away by these radioactive materials are pretty harmful. Now, these materials are called radioactive materials. We will talk more about them in our next lesson. Alright, so their nuclei change or decay by spitting out radiation in the form of particles or electromagnetic waves. So what they throw out may be particles or electromagnetic wave. Well, a better understanding of this will be gained in the next lesson. Here are some of the elements that we find around us, and if you click on one of them, the table will tell you if it is stable or unstable. If it is unstable, it will show you what happens. So here I have clicked on hydrogen H1. That is stable, just one proton. Now let's click on some of these and see what happens. Now this is carbon 14. Look at this. It became nitrogen 14. And is it stable? Well, if it is not stable, it will throw away something more. Now says nitrogen 14 is stable. Let's look at some other element. Now, this is unstable carbon 15. There it radiated, became nitrogen 15. And look maybe at oxygen 17. That is stable. It will not throw away anything. Let's see if this will throw away anything. Nitrogen 7. There you go. You see, look at what an unstable nucleus does. So, if a nucleus is unstable, it wants to achieve stability. And now, how does it achieve stability? By throwing away nuclear particles and energy. Okay. And this process is called radioactivity. We will talk more about it later on. There are three types of radiations emitted by a radioactive isotope. They are called alpha, beta, and gamma radiations. In fact, Rutherford used these alpha radiations to bombard the gold foil. So even before the Rutherford's experiment, the existence of these radiations were known. Alpha and beta are particles. In fact, this alpha is made up of 2 protons and 2 neutrons. So if a nucleus is too massive, it can throw away chunks of it. 2 protons and 2 neutrons is an alpha particle. When it goes away, well, it could create stability. If it doesn't create stability, it will throw away more particles until the nucleus becomes stable. So alpha and beta are particles, while gamma radiations are electromagnetic waves of great energy. Alright. Now, Rutherford model of the atom, is this a perfect model of the atom? Have we struck gold here? Do we know what atoms are? Well, no. This is only the beginning. There are problems with Rutherford model of the atom. You see, any model of the atom must explain the behavior of elements. Now, we know how hydrogen behave, how lithium behave, how helium behave. Some of the behaviors of these elements need to be explained by using the model of the atom. Now, Rutherford model actually failed in explaining many of the observed phenomena. But most of all, Rutherford's model failed because of a particular phenomenon. According to Maxwell's law of electromagnetic radiation, an accelerating electric charge should radiate energy. Now, if you look at the Rutherford model, what does the Rutherford model tell you? It tells you that an atom consists of a nucleus with electrons going round it in circles. Now, if you remember, we did talk about motion in circles. We said an object moving in a circle is continuously accelerating. Do you remember that one? And we call that acceleration centripetal acceleration. So an electron going around the nucleus in circles are actually accelerating continuously. And according to Maxwell's law, if an electron is accelerating, it should radiate energy. So an electron that is accelerating, if it's radiate energy, then it must continuously lose energy, and ultimately, if it loses energy, what will happen? It will fall onto the nucleus. You see, why is the moon going around the earth? Because the moon has a certain energy. It has a motion. Now what happens all of a sudden if the moon stops moving? It will simply fall into the earth. In the same way, an electron moving around the nucleus, if it loses energy continuously, it will spiral and spiral and spiral, and it will hit the nucleus. That means Rutherford model of the atom is not stable. An atom, like Rutherford says, cannot exist because electrons cannot continuously go around the nucleus without losing energy. And when they lose energy, they will fall into the nucleus. That means there is no more atom. An electron in orbit is an accelerating electric charge, and it should lose energy and ultimately fall in the nucleus. So these electrons are accelerating, and according to the Maxwell's theory, they must lose energy and ultimately the atom must collapse. So Rutherford's model is a failure because of this. Now, since this does not happen, well, if all atoms collapsed like this, then there will be no universe. There will be no matter, no substances, no elements. See? So we know that this does not happen. And since this does not happen, what is the conclusion? The model of the atom proposed by Rutherford is not correct. So there is significant problem with Rutherford model of the atom. Well, that really doesn't mean we need to discard it. What we need to do is to improve it. So we are now going to look at how we improve it. Now, a Danish physicist, Bohr, tried to solve this problem by linking familiar phenomena to atomic models. You see, once you take our familiar phenomena and try to explain it using the atom model, we can improve the atom model. And so we're going to now look at the model of the atom proposed by Niels Bohr, and I will do that in the second part of the lesson. All right?